Zoom link.
Yes.
Yeah, I think it's easy to think that it will just swap, but I think because there are different meetings, still it picks it up.
Yeah.
Yeah.
Okay, great. We'll get there. So how are you? Do you want to share anything with us?
I'm doing good. I'm doing good. Yeah, as we discussed, the setup and everything, pretty hectic, but we're progressing.
You're progressing.
Yeah, yeah, yeah. We'll talk, I think.
Yeah, sure.
Before tomorrow's session.
Yeah. I also have, well, see, yeah, I've got to take my dad to the hospital tomorrow.
Oh.
But I'll be back for the evening, I think. Yeah.
Okay. Okay, we can schedule.
Yeah.
Yeah.
See how we go.
Estimate to see where available. Hi, Simon. Hi, Ilaji.
Good evening.
Hi, everyone.
Yeah, we're good.
Ilaji, you're welcome.
Okay, so we're I think I've confused everyone because yeah, anyway, it doesn't matter. Well done. Some people are better at finding the Zoom studio room than I am. I was in the wrong room just now, so so without further ado, let me say welcome to session 8 of our PDC. And when we started this, to try and make 24 sessions sounds like a really long time to me, and I don't want us to lose the shape of what we're doing. So I'm trying to think of it in terms of 3 semesters, 8 weeks, 8 weeks, 8 weeks. And so this is the first 8 weeks, and we're going to do a little bit of revision and a little bit of overview, and then I'll take it all a step further forward. So I think there's these sort of components to permaculture, which is we're really talking, so far, we've been very much in the abstract, talking about the sort of big universal ideas. And this is the 4th session, is going to be the sort of the last one really of looking at things in that way. And we're going to drill down into much more detail in the next set of sessions. We're going to be looking at specific examples and so forth, and really beginning to think about how we can use permaculture design, apply it to ourselves and to our lives and our communities. And that's where it starts to become very powerful. So today, this week, is the beginning of that process. As we come to the end of our first semester, trying to take some of these ideas on board now and think about how we can use them. This is a very, very powerful tool that we are studying. And step by step, we're going to think about how to use it. Because, as we're finding out, is the real world's really complicated, and we can have ideas, but then to actually make them happen is another whole deal. So, let me find my... I also want to... Oops. Yeah. I'm going to talk about a few different things in this session, and I'm also going to push back to people watching this and think about your home situation, your objectives, and what it is that you want to achieve. And I'm going to give you a little flavor of what I've been doing over the last couple of years, and as a way of using some of these permaculture ideas. So I'm framing this PDC around, I keep referencing back to Bill Mollison's designer's book, and also using this sequence of principles as given to us by David Holmgren. And we're at principle 4, which is about, it's saying that natural systems have limits. They always have limits, they have a breaking point. And as we work with a natural system, it's constantly giving us information back. It's giving us feedback. So there's something about limitations. As we approach limitations, we get feedback. We get, which is information, and then we can choose what to do with that information. We're designers. We're trying to put ourselves, take responsibility for a situation and empower ourselves to make changes. So it's good to always have what our objectives are as well, from the outset. Okay. So I'm going to just show a few pictures of my world, and then you can translate that how it might relate to yours. And I'm going to say a little bit about Trevlack Farm. And Trevlack Farm, I don't own any land. I live in a house in a small village in a rural area. And for me to have land, have access to grow and to learn and keep with my permaculture, what I found is I've had to build relationships to other people who have access to land. So I've built gardens on public spaces. I built gardens on the orchards or food gardens, in community spaces or industrial spaces, on road edges, and always trying to find creative ways to solve problems. And permaculture reminds us to build mutually beneficial relations. And it's through these mutually beneficial relationships that everything becomes connected to everything else. And that's the other thing about limits and feedback. These two important ideas in the principle is it's leading us to think in terms of systems, which includes feedback. There's relationships. There's interesting things going on within it. Okay, I get ahead of myself. I want to tell you this story a little bit more. This little project came about because I wanted to learn more about soil and soil building. I wanted to learn more about the relationship between the quality of the soil and the health and the vitality of the plants that we grow in it. And what we're learning is there's a very strong relationship between the life in the soil and the ability of your plants to take up nutrients and also to access water. So this is something I felt that we need to understand better. And this is a farm. It's about 8 miles away from where I live. It looks a bit of a mess. This is on the edge of the farm, an area that they're working on and developing. There's an old barn and materials there. And I've been chatting to them about the possibility of developing a garden. And we wanted to do, say, for the soil, but also I want to demonstrate permaculture ideas. I want people to come and be able to visit me. I want to demonstrate, different techniques and so forth. And this is the right place to do it. So I've been visiting this farm and doing teaching and activities there for 10 or 12 years. So this hasn't come about quickly, but we can build long-term relationships built around, meeting mutual needs. So in the development of this corner of the farm, they also identified this building. It's an old, I don't know, I think it had chickens in it once, old, not very, great building, but potentially that could become a classroom, a reception area, a place where we can meet visitors and host volunteers. So I'm trying to think about bringing elements together to create a design, to create something that is I want to grow food, but I'm a teacher, I want a classroom, and I want volunteers to help me. So I can think about how I can begin to bring these things together to create a design. And if you like, to build a system. So this was my inspiration. This is a garden in Normandy, in northern France, at a very famous permaculture farm. and they grow very high quality vegetables, which they sell to restaurants in, I don't know, Paris or somewhere. The French appreciate quality food, and there's also a relationship between the quality of the soil and the taste of the food. So let's think again also about this idea of systems. Things are connected. Nature gives us feedback. So if we're growing plants and the plants are healthy and they taste good, we know we're doing it right. If we're growing plants and they're struggling and they're being attacked by pests, the garden's telling us something. We're not doing it right. We have to try harder, find other techniques. Anyway, this was my inspiration. And I drew a nice picture, and okay. So another, I think, an important part of working in partnership and working with someone is to make your intentions very clear so they can understand what it is you're planning to do and where you're going to do it and what your motivations are. And so I indicated on the farm approximately, this is the area we're interested in locating our garden, and the farm told us that they want to actually build a little shop area, a reception area for visitors here. And so the idea of having a garden next to that reception area made a lot of sense for them. So thinking about strategic location of something so that it functions with the other elements of the system. Farms are complicated. Everything that we have learned over the years of working with this farm is if you want to change one thing, it seems to affect everything else. So actually it's taken a year of planning and discussion to find the exact right place to put this garden and to come up with a management system of how we're going to look after it, and also think about what we're going to grow in it and all of those different things. So different elements to design. One of the things that we're interested in is a lot with building really good, healthy soil is the use of biochar. And I'm going to talk about that a little bit more this week in this week's session as well, because of all the things that sort of come across in the last 10 or 12 years, I think this whole biochar thing is about the most interesting and the thing that has enormous potential. So I'm also going to be taking you there and talking a bit about this. What's biochar, you might ask? Well, we'll come to that. It's charcoal. It's well-made charcoal. It's charcoal that's been made for the intention of not making nice big pieces for burning, for cooking, but for making like a dust, which you're going to use in your compost systems and your soil building systems. You would normally make this char from waste materials, things that old grasses or rice husks or I don't know, waste materials. So I want to build a garden. I want to do education. I want to have healthy plants that taste great and ultimately make a business. But also I want to learn. I want to use environmental techniques, which again is going to help give me more to teach about, more to study, and to benefit the results from. And we also know that if we have a carbon-rich soil, it can absorb more water. So these are all the reasons all the thoughts that I've got, the elements that I'm fitting together to build my garden. I'm not just thinking I want to grow beans and potatoes. I'm thinking about how do I build a relationship with the farm? How can I do my garden in a way in which I can use it for teaching? How can I make sure I'm building soil? Am I using interesting new techniques so that I'm learning? And on it goes. So because I wanted to do soil testing experiments, I thought it might be quite a good idea to mix the soil up to make it kind of uniform. And also I wanted to remove the weeds and the roots from what was in the field. So we put the pigs on it. We put a group of pigs onto it. And actually this shed here, this with the black roof, is a pig unit, and they breed pigs in there. And so one of our resources from the garden is the fact that nearby there's a pig breeding unit where there'll be lots of manure, and we can catch rainwater off the roof of the building. So if I've got water and I've got compost, I've got nutrients, I can gravity feed that to my garden. These are all parts of my plan. I'm thinking about, in a system, how to integrate different elements together. So you can kind of get a sense of where we are on the farm. It's a really beautiful place. This is our area. There's pigs, and that's after the pigs. They made a right old mess. Now, actually, I'm interested in no-dig garden systems. I don't want to disturb the soil, but I wanted to start off by kind of randomizing it, mixing it together. So that's what I decided to do. And if you get a new piece of land, you start a new project, you might want to do the same. But think carefully and be aware that if you get to heavy rainfall or something like that, that you could lose a lot of your soil very quickly. So this was how we started it. And then the next picture jumped to a couple of years later, but we shaped it into our, there's our classrooms come on as well. You can start to see the shape of the gardens really come together. And what we've done, I'm going to bring you back to this place in the future as we go through the course, because this is where I am doing my experiments. Half of the beds in this garden we have dug over, and the other half actually we haven't. We've gone for the no dig method. There's also the lower half of the garden we've treated with the biochar, which we made. The upper half we haven't, and we've added composted manure to all of the beds. So we're going to see over the next season or two if we can detect a difference between the dig, the no dig, the biochar, the no biochar. And you also notice in the middle here, I've got my compost area, and I'm making a very special compost, and because I want to make compost tea from it. So in making this compost, I'm thinking about bringing in materials from as many different diverse sources as possible, because I want as many different microbes as possible. And I'm going to, as I mentioned in last week's session, is a technique which we're going to be exploring in the next few weeks of the PDC, is not just making compost, but then brewing that compost to make a compost tea. And in the process, we multiply the microbes, those beneficial organisms that build the soil and make nutrients available to plants. That's actually what we're interested in. So I built this garden in a way in which it's close by my classroom. It's close to this is the new shop unit on the farm, and it's inside this black container here. They're developing these buildings to the side, and there's the pig unit up above. So actually, I'm in a great little location, and I've got all the resources I need to feed my garden around, and I can build relationships with the shop, the classroom, the public, visitors, and so forth. So there you go. There's a little flavor of my current project. And over the years, I've helped start off a lot of different projects in different places. Usually I do them for a few years and then end up moving on, starting again. We'll see what happens here, but I've got the framework of the garden in place. I'm ready now to start looking for volunteers and start having a regular 1 or 2 days a week where people come and help work on the area. And obviously, once we've filled this area with plants and we're on top of it, we might be able to take on other areas of the farm. So bit by bit, establishing ourselves and exploring how we can bring our permaculture into new places, into contact with new people, and keep continuously learning. Yeah, so it's a continuous process. Yeah, hi Nicholas. Sorry, I still haven't been able to. I don't know what's happening. This thing's crashed.
Yeah, I've been in touch with Nicholas and Igara, so we've been sorting stuff out, so they are good.
Okay, oh great, well done.
I didn't want to do the chats on the live
Yes.
feed to avoid interruptions.
Okay, thanks. Well done for that.
Yeah.
So, this is slides. This is by way of a recap, but I'm going to lead up now to the main themes of this set. And you remember I've taken you through these Holmgren principles. This we said observe and interact, catch and store energy, and that store represents that more than the soil. Think of the soil as a store of energy, but more than that it's a diverse habitat. And this article here is warning us about how agriculture is damaging soils, and this is the principal thing. Agriculture is about building soils. When we say permaculture is regenerative, that's what we mean. We're regenerating soils. We're building soil, adding carbon, building the capacity for plants to catch and store sunlight, because sunlight's the income that we all live on. Soil is key. Soil is the beginnings of of everything for our own wealth and sustenance. This graph is a reminder that the UK has, in 250 years, has transitioned from an organic farming foods to a system of either imported food or food grown on imported chemicals. So we are very, very vulnerable to global price instabilities. Britain either imports its food or imports the chemicals for its farming. I think that all communities need to move back or move towards a situation where they're producing a bit more of their food, and if you're doing 5%, aim for 10. If you're doing 10, aim for 20. And that's part of what I'm trying to find out. My exploration in the garden at Trevlack Farm is to see actually how much food can I grow one day a week of my physical labor with some volunteers. And I've got 20 raised beds, and the answer is I can grow some. It's not everything by any means, but it's a significant contribution. And I think as I get better at growing, I can grow a lot more food. So, and you remember when I said we're trying to develop short-term, medium-term, and long-term yields. Well, when you start a new project, the yields that come back to you are very short-term. It takes a while to build those, medium and longer-term yields. We talked about monoculture. We've talked about how when you plant lots of the same plant at the same time, they end up competing with each other because they're all got roots with the same requirements, the same root depth, in a sort of, in a big competition. Whereas when we allow ourselves to learn from nature, has plants with very different root shapes growing next to each other in a way in which they complement each other, create long-term stable systems. And this is our template, long-term stable systems. And in those long-term stable systems, the elements of the time to build those complex relationships. Like I have been building with Trevlack Farm for 12 years to the point where they've allowed me to, garden one of their fields and to bring volunteers and students there. This is what we're trying to do, is build long-term relationships and understand that's happening all around us. in nature and also in our communities. Here's a friend from Homer Bay making some compost, and I think reminding us that we're working that interface all the time to try and boost fertility. We're trying to make strategic interventions to return nutrients, to promote the beneficial microbes, to create the conditions that the beneficial organisms want, and understand that we're working with the elements on the land to maintain its fertility. We're starting to think more like systems. And also reminded you that every activity that you're doing, you're surrounded by your wider community. And if you can engage with, inspire, involve other community members, we like to say many hands make light work. We can achieve so much more working in groups and teams. And this is something we want to continue to build into our designs, strategies to build relationships with other people, create volunteering opportunities, catching and storing energy, building fertility, trapping water, exploring the relationships between different elements so that we're slowly building systems around us that nourish us. Systems that are designed to trap the available resource, and we can convert rainwater into fertile soil into the foods that we need. In this picture, we're also reminded is, as permaculture designers and thinking in systems thinking, we want to look at the whole landscape and understand that we want to trap as much water as we can into that landscape. We want to soak it into soils, it be absorbed into plants, into mulch in the ground, into watercourses, and so forth. And the more water we can hold in the landscape, the bigger the potential of that landscape to produce. So, understand all of these things are intrinsically related. We talked about swales, about putting elements in place by carefully observing the landscape, understanding the shape of it, understanding the shape and pattern of your rainfall, so we can put in passive systems that literally do the work for us continuously. So a well-placed swale, there's no flow sideways. The water will sit in it and soak into the ground. Contour catchment. So think about how we might keep adding elements into our system that reinforce the function of slowing down and catching water. Maybe there's lots of different strategies or things that we might want to put into place that's going to help us achieve that. So in permaculture, we say we reinforce key functions, water trapment, water soakage, with multiple elements. And so we have lots of different strategies in place to achieve that goal. Think about how they might reinforce each other. Building systems. Now, I think last week I showed you some of the pictures of Morocco and how just by slowing down water, making it go onto contour, it's slowly be able to build gardens and orchards climbing up the mountainsides. The only limit is your imagination, Bill Mollison said. There's potentially no upper limit to production, but your production will be held back by limiting factors. So if you don't have enough water, there's an absolute limit to what you can achieve, to what you can grow. So we need to really pay attention to these things. Okay, so that was a bit of a recap, and going back from a couple of weeks ago, and bringing us now to this idea of systems, how things are interconnected, how we can do something in one direction and somehow indirectly that makes something else happen somewhere else. Let's start with the biggest system of them all, and this is a very big idea. it's called the Gaia Hypothesis. Gaia, meaning, is the name for the Greek god of nature. And this was the Gaia Hypothesis, is this suggestion, this idea, this way of thinking was given to us by a scientist called James Lovelock. And in the very early 70s, when he first articulated this idea, people poo-pooed him. And over time, I think he's pointed in a direction that's made us understand that he was absolutely right. And there's a web page on the Sector 39 Academy website, and I create one each week for each session. I put on this week's session. There's an interview with between Morag Gamble from Australian Permaculture and a very famous physicist and author called Fritjof Capra. And they're talking about systems. And so I put the link to that YouTube video on the page because I think you find it very interesting. At the beginning, Fritjof Capra says, in his lifetime, he's been in this field of study for 50 years. He started out in physics and then moved more into being a writer and a science communicator. He says, in his lifetime, he's seen the prevailing worldview move from quite a mechanistic one to a complex systems one. In other words, 50 years ago, they used to think about nature, about the matter as a machine, and that we could sort of approach problem solving in a simple sort of A plus B equals C sequence of events. What we now know is it's not really the case. Everything's connected to everything else in a sort of dynamic way. So we create a change, and that might have many unexpected consequences, unanticipated consequences. Some of them might be good, some of them might be bad. Now, David Holmgren also reminded us, the sins of the father are visited unto the seventh generation. What he's saying is if we make mistakes, they might not be fully observable until, many generations hence. We need to pay attention to the subtleties. We need to understand that we might be causing ripple effects. It can be a good thing, or it can be a destructive thing if we're not paying attention and accepting feedback. So it's this accepting feedback, receiving the information that's coming back to us, analyzing it and trying to understand it. That's the key to how it all works. James Lovelock asked a very fundamental question when he actually was working for NASA in the 1950s. And he was on a team of scientists who were encouraged to think about, is there life on other planets? Is there life on Mars? James Lovelock thought about that and thought, well, how would we know? What would be the signature of life on Mars? And he thought about it, and he thought, well, certain chemicals would leave a signature of life. And in fact, the one that would most leave a signature of life would be oxygen. Oxygen is the most reactive element. It sticks to other things. It doesn't occur by itself unless it's constantly being created. So if oxygen wasn't being continuously released into our atmosphere, we'd run out. So it made him wonder, where did the first oxygen come from on our planet? And this leads us back into really the thrust of what this lecture is about, which is Lovelock's realization, which is life on Earth was created by life on Earth. The conditions for life are created and maintained by the life on the Earth. The atmosphere that we breathe has been generated and is maintained by life itself. That's what's so interesting. That was his big revelation. So here we have a look, looking through the Earth's atmosphere. And I've got a little scientific diagram here. Let's have a look at that. So there's the Earth, and then what we think of as the atmosphere, which is the troposphere, and that might go up anything up to 16, 17 kilometers high. The troposphere contains about 80% of all the molecules in our atmosphere. So it's much denser at the bottom here, and this is where all life is, and this is where weather is, and that's where all of the air molecules are in this troposphere. And there's a constant interaction between the Earth and the plants and the organisms on the planet and what the composition of this troposphere. As we go higher, there's this much wider stratosphere reaching up to 45 kilometers into the atmosphere. And this is what contains the ozone. And this is what filters out much of the ultraviolet, little asteroids and meteors or whatever, and space detritus gets burnt up in its atmosphere. It's the stratosphere that protects us a lot from what's out there in space. And there's a mesosphere above that, which is very, very thin. So 0.01% of all of the molecules in our atmosphere are in this mesosphere. So it's very, 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 would be very cold, and you wouldn't be able to breathe. So think about the layers of our complex planetary system. And we can also think, I wanted to get a little bit into thinking about evolution, because actually in design, what we're doing is we evolve a design. We can't have a concept or whatever. We might have the raw materials and we assemble them together, and so our design might present itself a bit like my garden at the farm. Let's just think about this, because if we go back to what geologists and scientists tell us about the formation of our planet is 5 billion years ago, it was a bunch of hot gases spiraling around. It slowly cooled down, and about 4.5 billion years ago became rock, and bare rock, no life. So what we can say is that over time, what we have seen is very simple life forms form on the planet, and over time that has actually grown into this amazing interconnected biosphere ecosystem that we are part of. I think in permaculture, it's very helpful to think about how we got here in the first place, because I want you to have an empathy with living and natural systems. Okay, so let's think about and to value every component. We're trying to get past this idea of goodies and baddies and pests and whatever. Let's understand that everything serves a function and has a role to play in this wider system that we are part of. So here's the timeline, and I've tried to simplify it because again, the real world is really complicated. So we try and understand it, try and make it simple. So here's a timeline that's 5 billion years long. 5,000 million years. That feels like a long time, right? 5,000 million years. Okay, what was their Earth like 5 billion years ago? It was a bunch of hot gases coalescing into the origin of Earth, which here on this sliding scale looks to me about 4.7 billion years ago. And how do we know that? I don't ask me, but they do. They have a lot of evidence. Now, this is really interesting here is when did life begin? And what they generally say is the first forms of life, very, very simple forms of life, started to occur incredibly early on the timeline, maybe as soon as 500 million years from the beginning of the Earth just being a barren rock. But actually, if you read around, there's also a whole load of discussion about, well, does that count as life? because there's very simple forms of life, which basically depends how you see it. But this also gives us an insight into something else, which is that right from the beginning, it seems that things on this planet seem to want to organize themselves into patterns. And there's some insight in that. So this is how biologists see the world, and an evolutionary biologist would see the world. So this is taking the really big picture at life on Earth. And what they might say is, if you look at, in the broadest forms of everything that could be regarded as a life form on Earth, they kind of break down into one of three categories only. There are things that are bacteria. There are things that are complex bacteria, as in single-celled species that don't have a nucleus. They just have their DNA floating around inside them. It's like a soup. And you've got complex organisms like us. And there's something else in between, the archaea. There's some strange, weird things that don't really fit into either category. And the thing that we know about this type of organism, the archaea, is they live in really hostile environments. They live where no other form of life can live. So, and they're made up of different chemicals, and they're really, really different from us. So that's interesting to think about, because all the indications are that the earliest forms of life, in inverted commas, happened deep down in the ocean trenches, volcanic cracks, where the energy of the system wasn't from the sun, but was from igneous rocks coming out of the core of the Earth. Imagine hot vents of magma boiling the sea, and that's somehow starting to arrange molecules according to heat and movement into patterns. And those simple patterns of molecules actually represent the very earliest, not really life forms, but organization, structural, molecular organization happening that begins to start to change the world. Let's just think about that. That starts the process of Gaia, of this evolutionary process. That we spent the last couple of hundred years trying to understand and realizing it's really more remarkable than anything that we could have ever imagined. If there is a God, and that God is all-seeing and all-knowing and all-powerful, that God would have created evolution, because nothing stays the same. Everything is constantly responding to its environment and also trying to modify the environment. That's seems to be the dynamic that drives it all forward. So I can come back to this. This is kind of, I'm going to just explore these three terms. Let's understand them a little bit better. So there's three types of life form. Bacteria, that's this one. They have cells, they have a membrane, they have DNA. That's the same of all three of these things. The bacteria and the archaea are also both unicellular, a single-celled thing. In the bacteria, the DNA is found free-floating in the cell. There's a membrane surrounding the cell. You find bacteria just about everywhere on the Earth. And they can be good, they can be bad, and they're absolutely essential in our digestion, and they're a very important part of all ecosystems. The archaea are made up of different chemicals. They have cells, membranes, and DNA, and they're unicellular. And you find them in hot springs, in volcanoes, in really salty water, in thermal vents in the ocean floor. Crazy things. And then there are the eukarya. We are eukaryotes. It means eukaryotes have, they can be unicellular, but mostly are multicellular organisms. They have organelles. There are structures within the cells that do particular functions, like mitochondria. The DNA is found only in the nucleus, and eukarya includes plants, animals, protista, and fungi. So that's just about all of the visible world, or everything that we can see is a eukaryote. But the eukaryotes are there because of the hard work done by the archaea and the bacteria that help manufacture the environment that we flourish in. I think that's a good way of thinking of it. Let's go back to the beginning. What did these early organisms look like? And, do we have any, are they still around? One of the very, very important, cyanobacteria, here you see it in this form, so it's the common ancestor coming all the way right back to here. A form of bacteria that can photosynthesize. A form of bacteria that can take energy from the sun to join carbon and oxygen together, and carbon and water together, and release the oxygen. And these types of cyanobacteria formed mats and rafts and created these structures which are known as stromatolites. And what's so interesting about that is these were the first organisms that started to release oxygen into the atmosphere, which was a waste product to them. The whole of our planet at the beginning was anaerobic. It was a carbon dioxide and methane environment. We couldn't survive in it. Only these really weird archaea could survive in that environment. Slowly, organisms came that started to change the environment, modify it. So this is a 3.7 billion year old fossil. This is one of the oldest, and it's of these rafts of this particular bacteria, these stromatolites, cyanobacteria. Is it a life form? Is it just a chemical process? Well, my old geography teacher used to say to me, biology teacher, he used to say to me, life is just a chemical reaction. And to a certain extent, we can see perhaps what he meant by that. It's energy from the sun coming in, or geothermal heat in the initial instance. And then that causes chemical reactions which create differences, which means it starts to leak oxygen into the atmosphere. So now let's go back to our timeline. On that left is your 5 billion years. Going right back to the origin of Earth, origin of life. And it says first life forms fossilized about 3.8 billion, 3.7 billion years ago. That's what we were looking at there. First photosynthesis. That's about 3.6 billion years ago. And then, which means that 3.6 billion years ago, life on Earth started to leak out oxygen, O2 molecules. And what happened was that those molecules reacted to everything. This was in the sea, in the ocean. And it can measure it very clearly, because at that time, there was a lot of dissolved ferrous compounds in the ocean. It was very rich in iron. Iron being one of the building blocks of life as well. That iron then reacted to the oxygen to create ferrous oxide or rust. And that's when all of the iron ore deposits of the world precipitated out into the shallow, warm seas. And that's consistent across the whole world. So, and that was then the beginning of, in fact, in some ways, that would have been a catastrophe. It happened over 1 billion years. So it didn't happen quickly. But slowly, as the oxygen, evolution created an oxygen-dominated atmosphere, all of those methane-breathing, sulfur-eating, weird archaea had to retreat underground into the guts of animals, into anaerobic conditions. So that's interesting to think about. And only just over 2 billion years ago, the first single cell plants came about. Well, okay, look, you can all look this up for yourself. It's a big old complicated thing, but what we get is, of 4.5 billion years of evolution, nothing happened for the first 500 million. The next 2.5 billion were basically green slime. Not a lot. But slowly, as those organisms lived and died, they changed the atmosphere of the planet. And only when there's enough oxygen in the planet in the atmosphere, can you have multicellular organisms, eukaryotes. That's us, that's plants, that's fungi, that's things that can move around, dinosaurs and everything else that came afterwards. So what was interesting was this happened about 600 million years ago, and it's called the Cambrian explosion. So most of what the visible forms of evolution, what we can see, all happened in the last 600 million years. And firstly all in sea, and then slowly, the first land plants and animals about 400 million years ago, amphibians, first reptiles, and on we go. There's different ways to illustrate this and to think about it, but this next image is my favorite image of understanding this, and we'll spend a little bit of time exploring this because it's it's a huge topic, and so this is exploring this picture. So the timeline is 5 billion years ago is in the middle, and the timeline goes both this way and that way. But also it's a logarithmic scale, or because remember that nothing happened pretty much for the first 3 billion years. So if we go up until about, if you see up until about a billion years ago, all of the life on Earth was archaea and bacteria somewhere deep down in the sea. And slowly, as it says, oceans rust, they started to release oxygen and create the atmosphere that we could then have eukaryotes. And you see the eukaryotes come in about 1 billion years ago, and then somewhere about 600 million years ago, the whole lot just exploded. And suddenly we have this enormous diversity of life on Earth. All of that has come about based on, whether it was 3 billion years of big green slime, basically, slowly built an atmosphere that then created life on Earth. There's been some big extinctions of diebacks. They've just put a few illustrations on here, but what they've mapped is the species that have survived. And what's interesting is, even when there have been big mass extinctions and dieback, is that evolution seems to come back with even greater diversity. So when there's change, what nature does is it responds by trying out lots of new different things. And it doesn't matter what it looks like. The question is, can it meet the challenges of the condition that it's in? So you can see that to be able to have these complex, interconnected living systems on the planet, we've had to travel a long way to get there, to build the soils and build the complexity that we need and the atmosphere to sustain that life. So this is a look, and there's us right down there, humans, the late arrivals at the party. We've only been around 200,000 years, remember? This is going back billions of years. So very, very interesting to think about this a little bit more deeply. So what James Lovelock realized was, on a certain level, we can regard our planet as a single living organism. It's interconnected because nothing's going anywhere, nothing's leaving the system. Things are just moving around. The atmosphere, the air that we breathe, has been created firstly by our ancestor organisms and now maintained by the trees, the forests, and the algae in the oceans, maintaining our atmosphere. So we can understand that at a certain level, the conditions for life are created by life. Now, if that's true on a planetary scale, that's true in your garden, that's true in your community. You can create the right conditions by strategically arranging things, trying out possibilities, but finding the best beneficial relationships, spatial relationships between the available elements, between the resources, to allow it to understand it's a living system and you are just the custodian of that. You're conducting the orchestra, if you like, not trying to control every element. So this is the Gaia theory is arguing that the Earth is a self-regulating living system. It's one that maintains the conditions for the perpetuation of life. From this, when Lovelock made this statement, obviously lots of environmentally thinking people then kind of said, well, surely we have an ethical responsibility to not damage this biosphere. That we need to perhaps a biosphere-centric way of thinking, or ecocentric way of thinking. We're all participating in managing this ecosystem, this living thing, and none of us are in control of it. We're only managing part of it. But we could look at a part of it and see it as a microcosm, a smaller version of the whole. This is at the heart of how we think in permaculture. Understanding that, we're empowering ourselves as being active participants in the custodianship of our ecosystem. We're part of this. James Lovelock said both living and dead organisms, as well as inorganic material, all form part of a constantly moving system that makes up the biosphere. So actually, even the minerals and the rocks, the water and the air being combined by life to create this biosphere. And it's the hypothesis that the Earth is like a self-regulating organism. Okay, so for some people this was very, very controversial. And because it broke this mechanistic way of the view of the world, our simplistic view of the world, the kind of view of the world that gave us the idea that we could put inorganic fertilizer on the ground and that would have a long-term fertility benefit, which it didn't. It had a long-term negative benefit. In the 4.6 billion years of its existence, the hypothesis states that Earth has developed into a self-evolving, self-regulating system. Now, we need to just expand on this a little bit because we're talking about limits and feedback. The Earth is a system, but it has limits. Look, here's the example that we've always given is just think about yourself and your own homeostatic functions, how you regulate your temperature. So if your core temperature rises very high a little bit, you get very, very ill. And if it cools right down, you can die. It's very, very important that your inner core temperature around your heart remains the same. So you are a microcosm of the ecosystem, of the biosphere. So if you go out and sit in the sun on a hot day, you perspire. That is a strategy for your body to evaporate heat away from your body to maintain your temperature. Your body shunts blood, all the capillaries in your skin open, and again, you can give off a lot more heat. That heat can escape your body. You can carry on doing that. You could seek out shade. You could have other strategies for cooling yourself down. But you can only tolerate that heat up to a certain level for so long. And beyond a certain point, you have a catastrophic failure. You pass out. You might die. Systems have limits. Obviously, the inverse happens. Put you if you go and stand in a fridge or a freezer unit, your skin all puckers up, the blood drains to your core so you don't lose all your heat. Your body might even sacrifice your fingers and toes. It doesn't even try and save them because it's trying to avoid that catastrophic failure. You start shivering and metabolizing energy just for heat and so on and so forth. So all of those things are feedbacks that's saying, hey, it's a bit cold in here. Maybe I need to relocate. Maybe I need to get a blanket. Maybe I need to light a fire. And when you're hot and sweat and panting, you go, oh, maybe it's time to get into the shade. So when we hit limits, we think about strategies to modify, to reduce that impact, okay? So think about how that might happen on a planetary scale. Think about how that might happen in your garden or in your home. You're aware that there are limits, and as you approach those limits, you get feedback. That feedback encourages you to modify and moderate your behavior, change your behavior. Okay, so I'm laboring these points, I think, because this is what feeds us into how we think about design. And I want us to think about how everything is connected to everything else, even if we don't quite realize it, even we don't understand how these connections might be, but for sure, that's all there. And we know from the Gaia theory, we know from the fact that the atmosphere has been created by life, that, in a very real way, things are connected. And as designers, we can work with that. We can work with the confidence, knowing of that the connections are there, even if we can't quite see them, even if we can't quite perceive them. We can know that by going about things in the right way, it attracts, if you like, positive energies in from other places. I'm trying to do with my garden at the farm. I'm trying to make it look interesting so people are drawn in and they want to help. I'm trying to make it experimental so it's more interesting. I want the food to taste good, so I'm rewarded for the work that I'm doing. So we talked a bit about mycelium. We talked a bit about the incredible connections that are going on beneath the soil between plants, but actually through this mycelial net. It's so interesting to realize that in this example, we have a Norway spruce, a particular kind of tree, and a European beech. And the spruce might be able to channel water through the fungal mycelium to the beech tree. It might send hormones or antibodies, other kinds of information as well as resources. So it's another way in which we can understand that things really are interconnected. Also, we have a litter-degrading saprophytic fungus. A saprophyte is something that eats dead material. So actually, this one is connected in the way it's there, ready to receive the leaf fall from the tree and to convert that into, again, ultimately into plant-available forms of nutrients. So again, it's holding the nutrients in the system. So as a designer, you're trying to think about ways to connect things together, ways to hold nutrients in the system. Understand that that's one of the driving forces of nature anyway. Here's a wonderful image I found today of, this is a root hair. Imagine the finest, tiniest tip of a root that you've ever seen. And then this blue, which has been stained with a dye, is a fungus that's growing, a mycorrhizal fungi that's growing in a close relationship with that root hair. look at the surface area, look at the complexity of that relationship, and then understand how many different exchanges may be going on between those different elements in the system. I found this image a couple of weeks ago, which I love, which is just showing the major river basins of Africa. We can see the Nile, the Congo, the Zambezi, Limpopo, and so forth. That made me think about how realizing that everyone in that Nile drainage basin system is connected to the same water system. Think about how enormous that is, and think of the connections might be there that we are not fully aware of, or how, and then also let's think of the responsibilities of those communities that live high up in the water catchment, because they are allowing that water to pass through their communities and then on to nourish communities further downstream from them. Your responsibility is to hold that resource in your ecosystem for as long as you can, get as many uses from it as you can, make it do work for you, nourishing plants, extracting the energy, returning it to its ecosystem in a better condition than it came to you. That water should be leaving you cleaner than it came. It should filter down through healthy, fertile soils, be re-evaporated through plants. So let's think about our responsibilities as individuals within really big systems. Think of the size of that whole Congo basin system that connects all of those people together without them really realizing it, without them being of how they're all together working on a team that they didn't know they were part of. Well, take a step back from that, and that's the same for all of us on planet Earth. We are all planetary custodians, guardians. We're not here to erode international cat, here to release its potential, to be regenerative. And then we'll take a break after this. It just brings us back to this absolutely key slide, so food web, that the system that we're coupling to is that system that through dead organic matter and fungi and this species make dead organic matter available, plant available, back to plants that can use the energy of the sun to try and transform that into the resources that we need. This is a product of an interconnected, dynamic system. You don't need to be buying fertilizers, and you don't need to be buying pesticides. You need to be understanding that a healthy ecosystem is balanced and fertile and dynamic. And that's the underlying, if you like, system relationship that we have. Okay. I was going to go into practice now. Gerald, what do you think if we have a short break?
Yeah, sure, we could have 10 minutes.
Yeah, we'll have, let's just see if there's any questions or any.
Yeah, sure. We can use about 6 minutes for the questions, and leave at at 50.
Yes.
At 50, then return back on top of the hour.
Yeah.
Anyone with any question?
Or Akko, just anything that's making you think.
Personally, I'm always, whenever I'm reading anything in line with Gaia, it's pretty interesting, and it's humbling and a constant reminder, as Steve said, by default, human beings are supposed to be sort of the leaders of the orchestra, but not owning it or not thinking that the orchestra depends on you or the choir depends on you. You're simply an integral part of it where you're supposed to behave as a part or simply support the system. Yeah, so that's always interesting. And if we have that, especially for the team on the course or even the people you interact with, we wouldn't be having all these crises and then chaos after chaos. Now you can, hear the story in Syria and Turkey being hit by earthquakes, mega earthquakes within the same month as they are still clearing the rubble, the bricks and the debris. Another, earthquake comes in to make things even more complicated. So all these are results of our actions that we are thinking, oh, we are superior, so we supposed to rule over and extract as much as we can from the earth or from the system. Any contributions, Simon, Hilda, Deborah? Okay. Okay, then. Let's use up the 12 minutes in break, but you may not log out. You can stay on, just mute, and then once on top of the hour, we'll go back. All right, see you then. See you shortly. That's in 12 minutes. We are currently in the break. Deragi, I think you had briefly logged out, but we're currently in the break and we are logging back. You can stay logged in and just mute. We are resuming at the top of the hour. Okay, so we'll alert everyone when we are back on 10 minutes from now.
So we had some interesting experiences this week with two of the Sector 39 team members traveling Nachivali refugee settlement and doing some training with them there. And be nice to have how that went. I noticed that Jean-Vier was there earlier, but he's disappeared now. So anyway, I want you to keep thinking about, so this theory, these sort of bigger concepts, this is what's going to frame our thinking going forward. I'm always wrestling to try and get people to think of the bigger picture and longer term, to think of permaculture and to see design as a series of steps that come with intention. So with understanding that systems have limits, and as we get close to those limits, we get feedback, we get kind of a warning, we get whatever, we get information comes back, whatever that might be. And we talked just last time just about the simplistic model of riding a bike and think how we're using information to correct the wobble all the time so we don't fall over. And we're balancing. So it's what we mean by systems running on feedback. So I want to edge us into now thinking about how we're going to approach design. And I'm going to give an example from someone else's project. And I'm also going to give you some hard beginning thinking tools to think about, again, how we approach design and understanding that we're working in systems, complex systems. So I found these pictures on the internet yesterday. I have not been to this farm, Limestone Farm, whatever, so 2017. I don't know the place. I've not been there. I'm just looking at some photos that I found on the internet, and I think that it illustrates our point really well. So that's all we need to know. And we're thinking about, I wanted to show an example. I don't want to get bogged in the details. I don't know about this project, but I can guess why they might have done certain things and that, would follow things. And that the first thing I thought when I looked at this is it's a lovely transition there from simplicity to complexity. Now, we've said that the evolutionary model is we start with something that's quite simple and slowly it evolves into something that's complex. We've talked about the strategic placement of elements. We've thought about how different elements reinforce systems. So these are the beginnings of understanding that there's relationships between everything in our system. I'm going to actually begin to enlarge on these. I'm going to start bringing some terms into our vocabulary, and we're going to use them more and more. We're going to understand them more deeply in the coming weeks. So don't panic if you're not keeping up, because for me, this is constant reinforcement. So far we've talked a lot about elements, systems, and functions, haven't we? We talked about that a system is made up of lots of different elements interacting with each other in some way. And the ecosystems have to fulfill certain key functions. So as designers, we would want to place elements that support key functions strongly. Second set of terminology I just want us to think about, if we're going to bring these words sector, zone, and elevation. And we're seeing evidence of sectors and zones and elevation in these pictures. And I think that's going to help us understand the process that whoever it is, the people behind this project have gone through. I showed you earlier how I was inspired by a project in Normandy, and I started a garden in Wales, inspired by that. I haven't been to Normandy. I don't understand exactly all of the reasons why they're doing what they're doing, but I can guess. Anyway, so it seems to me that whoever took on this farm probably took it on as it was. This is probably how they found it. And there's a house, there's a shed, there's a barn and a shed, sort of agricultural buildings. And I just basically seen grass around, not a lot going on, assuming they were doing some animal farming. And here we have a jump into the future, and we can see complexity. We can see they've brought in lots of different elements into their farm, and we might wonder what they're doing or how they might come about that. But clearly, from looking at it, it looks to me very patterned. And it looks to me like it's not been a random series of events, but that they strategically placed, what are we seeing? Polytunnels and greenhouses, and they've extended the existing sheds, and they've put in intensive gardens and orchards and look, things online. We can begin to speculate how the shape of the land might look, the contours, the elevation. Let's think of the shape of the land, and then what we might call zones, which is, this is a home zone, isn't it? So what might be the characteristics of a home zone? This looks like a work zone. So we might actually behave slightly differently in that. So the things that we might place in that zone might be different. And here, this one over here seems to be a growing system of some kind. So again, we don't know exactly the reasoning, but we can see that clearly there has been design and deliberate placement of elements to form a system. Okay. And we don't know again exactly, but we're bringing these ideas of sectors, zones, and elevation. So the sector being access, or the sunny side, or to be enlarged on. So think about how we could, using our permaculture design thinking, we might come around and observe this site, observe and interact. Let's see what we've got there. Let's interrogate the landscape. Let's start doing a survey and recording what's there, and thinking about what's there. And then we might go away and think about strategies to catch and store energy. What's our water catchment strategy going to be? Because we're going to want to know where water occurs on the site, how water moves through the site when it's rained, are there any streams? So think about that. Think about that might be a sector or a function, water catchment, water flow. Okay. Step by step. Permaculture, we're trying to use patterns to make sense of complex things, and so that we can communicate ideas to other people, build long-term plans that meet our needs. So that's what's going on here. What are we thinking about when we are looking perhaps at a plot, whether it's my garden or my home or a project or farm, it doesn't matter. These are really key questions that we might want to think about. Is it easy to get there? What's the access like? Will we be using vehicles? Building and maintaining roads is expensive. So look, this place is on a main road. That's very valuable. There's a tarred road, I presume, maintained by the government, or the transit authority. So good access, that's key. We need to understand that. because if we don't have it, it's a problem, or it will limit what we can do. What's the boundary of the land? We can only, and I get a clear sense of, you can see intense patterning of where they've arranged things spatially, but it suddenly stops. So I'm assuming that's the boundary of the land. That's going to greatly inform how we think about design, how we think about the site that we're looking at. Water's always a priority, because without water we can't do anything, and with too much water things get really badly damaged. So we've got to understand, our understanding of water is going to be related to the shape, the slope of the land, the topography, the shape of the land, and we need to think about buildings quite early on, because when we're thinking about and understanding a piece of land, we probably have limited places where we could put a building because of access, because of bringing materials onto site, because of the functions of a household. Buildings are a big investment; they cost a lot of money, or potentially materials, and so we want to get it right. And how buildings and slope and water relate to each other, and actually access, roads and boundaries, can be all part of our water management system. Buildings are very good at trapping and holding water, where's it going to go once it come off our roof? Can we hold it in barrels? Can we discharge it into a pond? Do we have a soak away system? These are the kind of things we want to be thinking about right at the beginning of the design process. So be clear about the boundaries of the land, that we can get to it, awareness of whether there is or isn't water, how water moves on that land, understand its shape, its slope, and having thought a little bit about whether we need buildings, whether there are buildings there, or the possibility to create buildings in the future. So limiting factors in design. This is a handout from a PDC from many years ago, from Chris Evans actually, and I keep coming back to this because it's a very useful way of thinking. So, and Chris tells us limits are the foundations of creativity. So what do we mean by that? Well, let's say you're going to build a garden and I'm going to give you a budget of $100. That's a limitation, okay? So you now got to be creative enough to design your garden that's going to cost no more than the $100. If I say you have $1,000, well, it's a different kind of garden. You buy plants in, or you can have people do the work for you, or £10,000 garden. That limitation sets your strategy. If you're trying to design a garden and you have only $100, there's no point in designing the $1,000 garden because you're not going to be able to build it. So we design to fit within limitations. We might ask ourselves, can I push on that limit? Is it really only $100? Can we get 105, 110? Could we have an event? Is there a way in which could we get good value for money? Could we trade? So even though that limitation then becomes the beginning point of our creativity. Can we problem solve within the budget? Can we stretch the budget by being creative? Can we win resources by doing other things? There's the example. Limits are the foundation of creativity. Limiting factors in design. Okay. As I said, we kind of come into it, we've got certain concepts in mind, we've got certain priorities in mind. Okay, that we're going to go onto our landscape. You're thinking of renting a piece of land for farming. You're thinking of locating your house, whatever it is. How are you doing this for a customer, maybe for someone else? Let's think about the limiting factors that might influence our design and how we might go about it. What is the land form that we're looking at? these are the visible things that we can measure and see for our science: the size, shape, aspect. Is it sunny? Is it shady? The slope. Can we explore the soils? Is the shape of that land? I guess as designers, what we're trying to think is the design has to speak to potentially those limitations. So if it's size, if it's really big, it's going to give us a certain type of strategy. We're going to have a maintenance strategy for a large area of land. If we've got a very small area of land, then we're going to be paying a lot of attention to detail, trying to make the most out of every square inch. So think about how those limitations have become the creative form for you. How can we use the shape, aspect, and slope of that land in a creative way? How can we turn that to our advantage? If it's very steep, we're going to have to come up with a certain kind of strategy. If it's very shady, that's going to limit us in another way. As designers, we're looking to understand what the limitations are and realize our design can push and pull and modify them. We can't get rid of it, but we can work with it. So where are we? Okay, we talked about our land. What's our climate like? And are we hot and dry? Are we cool and wet? Are we trying to get rid of heat, or are we trying to trap heat? We're going to have to come up with a set of strategies that are going to modify the climate locally. So if we're a place where it's a bit too hot and dry, we're thinking about shading, we're thinking about water trapment. If it's a place where it's a bit cool and wet, we're thinking about ways to trap heat, ways to create shelter and little protected microclimates. Here in the UK, we're always looking for south-facing protected walls, and we can grow plants up that where they'll get extra heat and a better solar aspect and be protected from the winds. But inversely, on the other side, we might have negative conditions. So we're using design to modify climate, soften it. It isn't quite as hot or quite as cold or quite as windy. And we're going to have multiple elements in our design that would be working towards that objective. Okay, one of our design objectives is to moderate climate. Okay, we're going to do that in lots of different ways. We have to think about water. Water is the ultimate limiting factor. So if I give you 1 million hectares but no water, I've given you nothing. You can't do anything with it. If there's no rainfall, or you can't trap that rainfall, so your strategy always is to prevent it leaving. You also need to think what will happen when the system's full and it's saturated. But we want to hold that water and slow it down so it can't erode. Understand how, if you've got lots of water, how you could use it. Aquaculture. You can affect the quality of the water by reed beds, aeration, nutrient extraction. If we're in a very arid area, we need strategies to recycle and reuse water. We need to increase the storages. How can we use trees and shading to prevent water loss? Or how can we organize our garden so that design so that we can shed surplus seasonal rainfall as well? What we've learned from soil and our study of soil is we can start with any form of soil in a very degraded or eroded form, whatever the pH, the depth, whether it has good organic content or not. But we need to know what our starting point is, so we have realistic objectives. But we can bring that soil back to life. And we can bring that soil back to life by improving its water, nutrient, content and holding capacity. Hey, that's the biochar, that's the compost. So, and as we increase the water of the soil and we improve our soil, then our whole ability to hold water and that also changes. And our ability of soil and water affects us to change microclimate by using different kinds of plant species that create more shading and more evaporation. So again, think about how all of these factors are interconnected. They're interconnected, and by addressing limitations, we raise the possibility of the whole system. So each time you remove one limiting factor, then the next one might present itself, and then you can address that. So there's going to be all sorts of limiting factors around your soil and soil quality. And in your design, you need to create strategies that address that so that you're building soil, creating the right conditions to favor the plants that you want to grow or the animals you want to keep. So obviously between climate, water, soil, landform, well, vegetation sits within that. If we want to understand a bit of land, what do we learn from the vegetation that's there already? How can we extend, make the most of the growing season? Can we make it a little bit longer? Can we make it start earlier? Can we create more diverse vegetation? Can we assemble our plants together in guilds, in mutually beneficial relationships? Can we carefully select and strategically place vegetation in a way in which it supports other functions of reducing those limiting factors? We want a bit more shade, a bit more humidity, a bit more compost. Think about, we're going to choose elements when we get further into our design, we're going to choose elements that speak to and reinforce all of the limitations in the system. Animals. Many animals can be incredibly destructive in a system, and they can be very beneficial. So they need to be integrated into the system itself. Animals unrestrained, if you like, without channeling their energy usefully, they can be very destructive. But in the right use, in the right way, they can be an engine that drives the whole system, because animals can process a lot of vegetable matter, create materials for compost and manure. They can do work, they can trample on things, they can pull a plow, they can contribute to economy in many different ways. Can we explore different breeds? Can we have really healthy animals by having them integrated into a system where they have, better choice of nutrition? Let's think about, these are all of our design goals in permaculture. And then the last two around buildings and energy. Buildings themselves, they're designed to be climate modifiers. It's cool inside and it's warmer outside, or whatever. Or it's warm inside and cooler, depending on your climate and how you set up your priorities. Buildings represent a significant investment of resources and energy. They're going to have to be maintained. How can we minimize those as being limiting factors? Can we strategically place buildings so that they have other impacts, beneficial, and understand that strategic placement of things like buildings will have a long-term impact on the rest of the site. And these are things we need to get right, because they can become significantly frustrations. So these are limiting factors in design, the sort of visible things, how we might then begin to start thinking about designing and building our own permaculture system. I like to say is, the natural state, I think we encourage to think like this in permaculture. It's the natural state of things in the natural world is its abundance. Left to itself, 4 billion years, evolution gave us rainforests, gave us, a zillion species of fish and birds and what have you. It gave us absolute abundance. So the building blocks are there. So one way we can think about it in permaculture is, well, why isn't a system abundant? It's being held back by limiting factors. It's the thing that's holding you back, me back. What's the thing preventing us from being successful? Is it the lack of tools, or the lack of information, or the lack of access to land, or we haven't got enough water, we haven't got enough energy, there's not enough hours in the day? If you could start to remove those limiting factors, then you get a spurt of growth. If, I haven't got enough time and knowledge to achieve my goals, well, I can build relationships with colleagues, with friends, with community, with family, and I can begin to change that. As permaculture designers, our ideas, our challenge is to remove the limiting factor, the thing that's holding us back from abundance. The natural state is abundance. How do we get there? Well, we're also reminded by Chris Evans, is sometimes the things holding us back are invisible. And maybe addressing the visible limitations is, that's one set of things. Okay, we haven't got enough water, let's put a water butt in, let's do whatever. But maybe there's invisible factors that are holding us back. And I think often it's those that we perhaps forget to address. And sometimes those are the things we need to invest our energies into. The things that are enabling the system to form itself. What's holding us back? Is it financial? For all of us, if we had more money, we could do more. We're all aware of that. We're being held back by financial constraints. What can we do about that? Well, access to finance. Could we have savings and loans clubs? Can we start credit unions? Can we trade? Can we generate a bit of wealth? Can we be more frugal? Can we save on what we're sending? Can we create more of a cyclical local economy? Can we add value locally to what we're doing? I don't know. I mean, that's often the limiting factor, isn't it? But just sitting there waiting for someone to give you money that's not going to cut it. If we're creative, we've got to create designs that sit within the limitations. So be realistic. If you have very little money, your design is going to have to cost, it's have to act within that. But how do we make the best value out of what we do have? I think that's the key thing all the time. Okay, invisible factors might be around communication. Hey, we can't even speak the same language. Maybe we haven't got education. Maybe we haven't got access to technology, media, whatever else it might be. But again, we can work on that. I think the communications comes from, I think that's why the PDC is so powerful. It's an education thing in which we are finding a language and sharing technology and ideas so that we can overcome that obstacle. And if we can come together as a group of people, we can challenge the financial limitations a little bit better because we can share, we can pull together. We have a louder voice. We have a slightly bigger pool of resource to draw from. There might be political factors that are preventing things moving around, whether they're personal, party political. Can we align ourselves with local initiatives? That's what it means by Agenda 21, but other local policy initiatives that we can gain a bit of traction from. Let's try and find where the energy and the momentum is. We're doing permaculture. We're helping people. We're helping ourselves. We're helping community. We're helping the environment. So why wouldn't people in the political sphere want to, in some way, help us? Can we communicate and show to them also how it is that we're contributing to the wider system? Limiting factors caused from social sphere. Now, there's a lot of these, and I think this is an area in people care. The people care side of permaculture is that we need to invest in. Very seriously important area is, okay, for your initiative that you're trying to design to be successful, you don't want there to be barriers for inclusion from the surrounding society. You don't want there to be barriers to inclusion from potential stakeholders, volunteers, partners. And sometimes that takes an active process to understand what the barriers, what the limiting factors actually might be for certain groups. So it might be a gender. There might be some gender specific, do women need particular facilities, space, maybe different cultural habits, maybe reach different audiences by different routes. Let us not let our beliefs divide us. I think that within permaculture, our focus is to find what we agree on. Is to find where's the overlap, where's the harmony point. Hey, we've all got to eat. We're all trying to translate the sun's energy through plants into food. We can collaborate on that. Our beliefs don't need to get in the way. You may be a Christian, I might be a Muslim. That doesn't actually affect the biology of our situation. And as we find commonality, we can explore each other's cultural richness, embrace diversity in permaculture. Religion, cultural habits, different ways that people might maybe participate. There may be taboos around aspects of what we're doing that we're not aware of. So again, this is a communication and feedback thing to understand where those little cultural edges or barriers might exist. And we're only going to uncover that by interactions, by, exploring that. The other one he's got here is the legal things. There's laws, grants, ownership, I don't know, probably all sorts of, and also customs and traditions that might define behaviours. But again, it's our job as permaculture designers is to push at edges, to soften these limiting factors, to find ways to get because sometimes these overlap areas where the edges lie are very productive areas too. And if we can get over some of perhaps social taboos or political disconnection, if we can sometimes get past those, then suddenly a whole flood of resources and energies can come our way. Now you've got to remember that we're not wrong. We're trying to through permaculture, we're pointing out to people water flows downhill. We're pointing out to people that we're all connected by the air we breathe, the water we drink, the food we eat, the soil that translates the dead organic matter back into living organic matter. That's what binds us all together, and that's our collective endeavor. Okay, so limiting factors in design. And a reminder, these PowerPoints are downloadable from the Academy website. So you can take notes, or you can always come back and look at these. And I've been working with some of these models for years, and they slowly reveal themselves to you as you keep thinking about it. And there's a logic and a sequence to how we go about design. And remember, it all began with ethics and values. And ask the question, how do we meet our needs? And what's the difference between a need and a want? Okay. So I thought it might be fun to dip in and out of these next couple of pictures. And this is we're having a bit of fun. Okay, I haven't been to this place. I don't know exactly what their goals are. I'm making a guess. So imagine it's like a parlor game, but it's like a permaculture parlor game. And let's try and understand what it is that these people have been doing on this land and why they might have done it. And so we've seen, just to recap, we've seen this transition from a kind of a nothing to a stepping stone and we're going to see how it is in present day. So, which is like this. What are we seeing? Well, we're seeing, obviously, we're seeing design and we're seeing strategic placement. So I can tell you about the slope. This is the highest point of the land and this is the lowest point. So if there's water's going to flow, it's going to go downhill. So what are we seeing is they strategically arranged these beds and whatever these plantings are and whatever these things are, they all seem to be on contour. So they've added other elements. We've got access route here. This looks like animal pens. We've got a car access route here. And then we can see these beds and all these plantings here and a field edge here. And then this looks like a forest garden type thing down here. It's all on contour. I suspect this is all part of their slow down water, get a lot of energy, get as much yield from it as possible strategy. So strategic placement of elements to support key functions. And again, and those functions come in an order of priority. Things that we can't change, we need to pay attention to first. So access. Here's a road paid for by the government. So we're going to make as much use of that as possible. We can get onto the farm here, and I don't know about here. So we've got good access, and this road comes all the way down to here. Now I notice we have an intensive growing area here. We seem to have chicken units or duck units there. This, I read from the notes, is a classroom education area. So again, I'm seeing visitors coming to the site, accessing in through this road, where they don't need to come to the house, a private house where the people live, and people can come to study, to work in the workshop, to access the gardens, visit this work area. And so you can see that all of this is a work zone. And all of this separates out the function of people coming to the farm for farm business and people coming in and out of the house for house business, for home. It might be a slightly different people, different function. I'm seeing next to the house intensive raised bed gardens. So what would you put? So if this is the home, this is where the people are going to spend most of their time. We might call this zone 1, to use the zone terminology. So as we step out of this garden, out of the home, here's our intensive garden, which is between the home area and the work area. So this is like a zone 2 garden. And what goes on in zone 2 supports the home function in zone 1, but it has a relationship to the work function here, the workshop, the study classroom, and this animal area. This all represents zone 3 work. And this also looks like productive areas. We can go back to their map, to their plan. Well, I can't quite read that. Oh yeah. I'm seeing outdoor ovens, sensory garden. They've got all sorts of things imagined. They've got water catchment off that roof. They've got elements here to support visitor functions and so forth. And if we carry on to see, this is the most up-to-date photo they published. Again, to say, I haven't been to this place. I don't know anything about it. I'm looking at it and I'm seeing how they've enhanced their design. Their buildings are now catching and storing solar energy, and I can see water tanks. So they're catching the sun, they're catching the water, they're creating a home, they're fulfilling that function. We've got this lovely garden now really established next to the house. But look how these hedges now have grown, so the house is private from the road. It's supporting the function of being in the house. This looks like a little private family garden down here. And clearly this is a zone 4 orchard forest garden area that we've got here too. So what we're seeing is it's a farm. It's fulfilling certain functions, including home and housing, work and workshop, trainers and students, and then animals and livestock, and different growing systems. but they've all been arranged in a way in which there's an interrelationship between them all. Water every drop of water is held in the system as long as possible, and it's not allowed to leave until it's visited all the different growing areas of the farm. Think how many strategies there are for catching and storing energy. Different growing systems. They've got perennial growing systems. They've got annual growing systems. They've got small livestock. They've got ducks and chickens. And we've seen the forest, and on it goes. There's features in there that support the people within it. So there's going to be tool sheds. There's going to be cooking areas or recreation areas, and understand how each one of those elements would support a wider function of the design. So we're going to give you, over the next few weeks, I'm going to show you more examples and models. I think it's really good is to see examples from different places in different climate zones. I think this is in Australia. I think this is New South Wales, Australia. I'm remembering now from my reading. And the sun comes around like this on the north side. So in terms of the sectors and this is the lowest part as well. So all of this is bathed in the morning light, and then in the evening, the sun would be on this side, and this would capture the evening light. So see how gardens are aligned spatially to trap as much as the sun, take a best advantage of the conditions. So permaculture design, fulfilling multiple functions, but creating a system that catches and stores every bit of energy and holds on to it for as long as possible to create a big diversity of different yields. Okay. Any questions on that or any thoughts on that? I'm going to carry on to the next thing otherwise, but I want to show you, I've showed you two examples now this week. A little bit of my garden at the process I'm going through. And then we've seen this example of this farm in Australia and how they've used design. So it might be interesting to consider what were the limiting factors of this farm right at the beginning. Is there's no shadow, there's no shade. So think how exposed everything is to the wind and the sun. It gets hot in Australia. Also, they can get heavy rainfall at times. So, and there's no sort of functional relationship between those elements. And what's so clever is as they've filled in the spaces between the buildings, they've added shade, they've added protection, they've added privacy from the road, privacy from visitors, and added to the functionality of the place. So all they've done is keep adding, and they've put strategies in place to minimize the limiting factors, and created through consultation a visualization of what they want to do, and then they've implemented that step by step over a period of many years. But the clever thing is they stuck to the same plan the whole way, because that's what there's only one right place to put things. So if you've got it in the right place, you don't ever need to move it. The sun isn't going to change its arc over the sky. Water's always going to run downhill. We're always going to be working with these same primeval forces. That road there isn't really going anywhere. These are kind of certainties that we can then hang our design around. So the limiting factors are what inform the design process. Okay. continually fascinating process to work with these same permaculture principles. I think that the core ideas are not massively complicated, but what's interesting is because reality is complicated, because every circle we apply our permaculture design tools, that circumstance is going to be unique. Because the shape of the land, the angle of the sun, the climate, the rainfall, it's going to be unique. The soil type, it's going to be slightly different there than it is somewhere else. And then the people involved, they're going to have different priorities. They're going to have different skills. They're going to have different amounts of time and knowledge available to them. And they might have very different priorities of what they want to achieve. So also understand is permaculture designs are very personal. They reflect the site, the stakeholders, the participants of the process, and it should be an expression that meets their needs. So I can't stress enough when we think about the social and personal needs of people to create an inclusive space, thinking about gender issues or age issues, sexuality issues. I don't know, there's so many different potential religious, cultural. How do we make people feel welcome? How do we create an inclusive space? I think that's that. And if we can factors, then we find labor force to shape, to visualize, and then shape and build, and then live in that design. Imagine in that farm in Australia that we've been looking at, all those little niche and take part in that project. Before it might just be one guy on a mower or a guy with a couple of cows. But now suddenly we've got all of this diversity. We have niches, lots of, there's education function, there's the food growing function, there's the building maintenance, there's the harvesting and the growing and the, who knows, all the different, the communicating of knowledge. I could think of all of the different activities that might be going on within that farm. Okay, I say it again, there's potentially no upper limit to productivity, because once you've got a space like that, you can keep adding into it, little pottery or, I don't know, a brewery or, I don't know what, things that retain to skills and knowledge, art, creativity. All of these come once we've got the key elements in the right place with those basic building blocks. And we can then continually and strategically remove the limiting factors. That's how that's how I'm trying to, I guess I want to make you think. Okay. I've got another line of thinking. And I mentioned about biochar. I'm going to talk about it a little bit more again. It's also talking about soil. Soil is an interconnected system. Soil is a living dynamic matrix. Soil as a limiting factor in our own human potential. If we haven't got healthy soils, we can't produce healthy food. We can't translate solar energy into resource. I produced this slideshow for a competition about 10 years ago, and they wanted us to create a product, and that was part of the competition. We were trying to think of a really deep environmental product, and this was the presentation that I put together, and we called it Garden Planet Biochar. And our thinking was, we didn't get picked up. We didn't win the competition. It was too complicated for people, but I'm still working on this. Sometimes it takes a few years to get something right. So I just touched on biochar. Well, it's charcoal, but it can be a very low value form of charcoal in like dust. And we're going to use it in our garden to increase our soil fertility. And indirectly, that's going to affect the whole planet because everything's connected to everything else. That's why we called it Garden Planet Biochar. It's way too clever for most people, I think, but once you begin to understand what soil is, the life that's in the soil, and the fact that biochar creates habitat for that life in the soil, and then you realize how that's going to affect you locally and globally. So that's where we're at. This is my pitch for my product. And we call it a bioactive soil enhancer. Now that sounds like mumbo jumbo. It's the kind of thing they do put on products. By bioactive, I mean it's alive, it's biologically alive, and it's going to enhance your soil by enhancing the soil life. So, welcome to my product pitch. Welcome to thinking about biochar, and welcome to thinking about biochar of how it might contribute to a whole system, because that's our theme. So this could be a keystone technology in the fight against climate change. There's my pitch. This is really big. This is enormous, actually. Really, really big deal. Climate change is a global problem. There's too much carbon in the atmosphere. Biochar offers food security and stable soils. That's to a westernized society like us here in the UK, where we don't grow food, we buy it in shops. That doesn't really tell us anything, because we equate food with money. We don't really think about where food comes from. Food comes from shops. If you have money, you can buy food. So no one's interested in soil. That's because we're not thinking in systems. We're not realizing it's all joined up. My ambition with this would be to make biochar accessible to all people, for them to understand its importance, perhaps to one degree, but to be able to make it and use it themselves. And the more we thought about this, it gets complicated, because to make it efficiently, you need some kind of a kiln. But as soon as you do that, you then take it out of reach of most people. So biochar. Is this the way we change the world? It has that potential. It's that big. Okay. Let's go beneath the soil. This is our journey now. We're down into the soil. Here's our photosynthesis. Here's sugars being created by carbon dioxide and water being joined together. And that process is only happening because there's a whole matrix of life in that soil that's cycling nutrients and making them available to the plants. And then we've already explained is we need 4 or 5 trophic levels of soil life, not just the bacteria. We need the things that eat the bacteria and the things that eat the things that eat the bacteria for that to then start to become an ecosystem. We're partnering with the soil food web. If you don't want to buy fertilizer, you don't want to buy pesticides, you don't want to have to buy import water, you have to partner with the soil food web. You have to become part of this soil-based system, okay? And as we go down into it, we realize all these crazy things living in that soil that we didn't really know about, like mycorrhizal fungi. Now, you've heard of them now because I mention them just about every week on this course. There's miles and miles of fungal mycelium in every cubic centimeter of soil. So we don't want to disturb the soil. We actually want to enhance the conditions that promote the soil food web. We're now farming by partnering with the soil food web, okay? Here's our little pine seedling with its little brown roots. We can see every one of these white dots is a node point of mycorrhizal fungi, and it's sending its fungal hyphae out in so many different directions, multiplying the surface area of the roots, creating an edge where the plant can hold onto the soil and start to have a conversation with all the soil microbes and start exchanging nutrients and accessing the available things there. There's mycelium create little micro cavities where little communities of other soil microbes can exist. They exude their glue, and they kind of stick themselves onto the soil, the mineral particles, onto the fungi, and create an interconnected living matrix that is soil. And we also understand that carbon is cycling through that system, through the leaves of the trees, the stem of the trees, the roots of the trees, and ultimately ending up long-term in the soil as organic matter, soil carbon. And also, look at this interesting exchange, carbon dioxide coming off the land, 2.2 tons per acre, and carbon dioxide being absorbed through photosynthesis, the grasses and trees, 2.9 tons of carbon per acre. Some of the carbon in the system is woody debris lying around. Again, that's going back to the atmosphere as carbon dioxide. But in our cycle, 45% of the soil organic matter ends up in the soil. That's the carbon. And we want at least 3% organic matter in our soil. And we're going to achieve that by doing compost and biochar. This is a picture from the UK. And on the right-hand side is the land has been treated with, I don't know if it's compost or biochar, but it has enhanced carbon, increased carbon loading in the soils compared to on the other side of the river where there isn't. What we're seeing is weaker crop, a drier soil, and lots of erosion. On this side, we're seeing the riparian edges remain stable. We're seeing no erosion tracks from animals and a greener, healthier soil. It's not conclusive proof. This is not very scientific. This is just anecdotal, but we're seeing the patterns. We're seeing there's a relationship between the carbon in the soil and the ability of that soil to nourish plants. Much of the planet was forested. When we humans come around, the first thing we do is we remove the trees. These trees, 1,500 years old. They've been standing there for over 1,000 years. That soil beneath those trees has never seen the daylight in that time. So as soon as we start ploughing that up and interacting with that, we're releasing huge amounts of stored carbon that's maybe built up over long periods of time, which is why we, in our permaculture systems, we're looking to not disturb the soil and to return a lot of the tree cover that was removed back, but we're going to do it in a way in which it supports the functions of growing the plants that we want to grow. We don't shade out our whole garden. It can be strategic placement to support function. This was the game-changing book for me. It's called The Biochar Solution, Carbon Farming and Climate Change. And it's written by Albert Bates. Albert Bates is a very active permaculture teacher in North America. He does a lot of stuff in the Caribbean and Central America. He's also part of the global eco-village network. Albert's a polymath. He's a genius in lots of different ways. He's written books on various different subjects. He's a really, really interesting guy. We need more people like that in permaculture. Albert got onto the biochar story really early on, and this was the first book that came out of this research, and it's just, for me, it was a game changer. It was fascinating, and I'm going to take a little bit of time to enlarge on this. So here's the story: is biochar comes from the Amazon rainforest. Something that people observed there from when they were clearing the forest and revealing that there were these black soils, terra preta, these black, dark soils under the rainforest, which you don't get black, dark soils under the rainforest. You don't get a buildup of organic matter because that organic matter is constantly, it's breaking down the tropics. Organic matter is breaking down faster than it's returning. So when the people first came across this, they were actually create an absolute dilemma. And it's because these soils are man-made. Or there's no explanation for them. But when people looked at these black soils under a microscope, they're full of not just particles of charcoal, which they are, but also bits of broken pottery. Clearly a lot of human interaction. So here's the confusion, is that it has always been said by anthropologists and historians, but that there could never have been a significant civilization in the Amazon, in the rainforest, because you can't farm rainforest soils. And it's always been a contention that you can't have organized complex society without agriculture, because you need a surplus of food to support a labor population that's involved in non-farming activities. So the assumption always was that people are basically hunter-gatherers in the Amazon rainforest because they don't have any other life choices. This turns out to be completely wrong. And there was large settlements in the Amazon rainforest, and there's evidence for it everywhere. And this created a kind of a dilemma or a polarization of views. There cannot have been a major civilization in the Amazon rainforest because you can't do farming in the rainforest soils. So either I'm right, or this view is right, there was no civilization in the rainforest in the Amazon, or if there was, they would have to be the most sophisticated farmers the world has ever seen. Well, guess which one it is? Turns out they were the most sophisticated farmers the world has ever seen in the Amazon rainforest, right up until the arrival of the Spanish conquistadors at the end of the 16th century, which brought smallpox and influenza, and many people, 95% population, died. This is what it says in the Biosphere solution, as it tells a story, and I think it's worth telling, is a group of Spanish, let's call it adventurers, arrived in Peru on the western coast of South America. And they formed an expedition, I don't know, let's say with 50 or 60 men. And they climbed up over the Andes Mountains, and they came down the other side. And they were the first Europeans to see just the rainforest that goes on forever. 2,000 miles of non-stop, verdant green. They saw streams that became rivers, and rivers became almost like inland seas. And they decided to explore. And the further they went into the landscape, the harder it was going to be for them to get back to where they came from. They built a raft, and they went down some of the rapids and the rivers. And eventually then they came to a place where they stopped and they built a boat. Some of the sailors walked back into the mountains and found iron ore, while the others made charcoal, and they smelted the iron ore to make nails. And with the nails, they built a boat. And with the boat, with that ship, they sailed down 2,000 miles of Amazon out into the eastern side of South America and round to the Caribbean. and he didn't lose a man. I think it took a year and a half. And but the interesting thing was the Spanish sailors on this boat sailing through the Amazon, 1500 and so, reported in their journals that they saw cleared land, fields, cities sparkling white in the sunshine. This was complex civilization. Sometimes they stopped and they went into villages and they found whole villages empty because people were away working in their fields, and they saw generous stocks of food and their squashes, and I don't know what they had, and the sailors would raid the food and run back to the boat and carried on. Clearly a highly developed, complex society in the Amazon. How did they do it? Well, they learned how to build their own soil. And the fascinating thing about this culture, and if you think about it, is they died off. The diseases brought in by the Spanish, they died off. So their land that they had cultivated was suddenly swallowed back by the jungle. So they disappeared. The only evidence they left behind that they'd ever been there was the footprint of fertile soil. I don't know of another society on Earth that has done that. So one of the interesting observations is in those areas of what we used to think was wild jungle, like just random association of plants, actually there's a proliferation of edible fruits. And that's because what we're actually seeing is a managed food forest system that was maybe managed for thousands of years that's then that's now gone wild because we lost the population. So large parts of the Amazon rainforest is maybe only 500 years old since the loss of these people. Parts of it even could be said to be man-made. Underneath the areas where there was settlement, we find these very stable, fertile black soils, terra preta, carbon-rich soils. And these guys had built over thousands of years. So they've been farming some of these areas consistently for, I don't know, more than 2,000 years. You can radiocarbon date carbon fragments. So they can see exactly how long they've been going there. They can see the pollen grains trapped in the soil. They can see they correct long-term sustainable farming systems that had stacked away tons and tons of carbon each year. How did they do it? How did they make terra preta? What is it? To be honest, no one really knows because the society died out. But we can come back and observe, and we can understand the processes that they used, and we can try and copy them. And we can think about how we could interact with the carbon cycle in a way in which we could be learning lessons from what our ancestors had done, and we can be seriously addressing the carbon problem, the global problem. We don't need to worry about the global problem. We have to solve the local problem. But when we solve the local problem, we contribute to the global problem because everything's connected to everything else. We're in a closed loop system. Here's our carbon cycle. We've seen this more than once now. Here's our tree photosynthesizing, building biomass. And think about how that biomass decomposes or burns, and 99% of that carbon is released back to the atmosphere as CO2. So there's a gradual, slight sequestration, but it's very, very slow process. Permaculture, we want to speed things up. We want to, as designers, we're going to make strategic interactions to increase productivity. All we're doing is, instead of allowing the biomass to decompose slowly to rot away, we interact with it. We take some of that and we pyrolyze it. We heat it up. And from that, we get two things, two outputs of pyrolyzing organic matter. is you get wood gas, syngas, you get biogas comes from it, a bio oil, which we'll go into, a flammable gas, and what's left, you get about 50% of the carbon part remains as the biochar. And so obviously driving off the gas, releasing the energy form, puts that half of that carbon up, 50% of that carbon dioxide back into the atmosphere. But you've now diverted maybe half of it into this char form, which is going to remain stable in the soil for thousands of years, just like the terra preta. So the way we solve the climate change problem is, number one, we stop polluting. We stop burning coal, gas, and oil. No more. We move away from that as quickly as possible, strategically. As we reduce our emissions, we can now begin to think about sequestration. And plants are the best way to draw down carbon out of the atmosphere and put it into a form in which now we can lock it up and build long-term fertility with it. So I'm going to just talk a little bit about combustion, about how we burn wood, and this is a traditional oven built out of very heavy stone, and this is designed to catch and store the heat of the combustion of the wood. And this is the key thing I think that I always want people to understand, and is the hotter you burn wood, the more energy it releases. Because actually, a scientist friend of mine said to me, look, wood doesn't really burn. Think of it more as it thermally degrades. So instead, as if we heat wood up, it gives off a volatile gas, a flammable gas. The hotter the wood is, the more it gives off the gas, and the more efficient, and that gas is flammable. So, and the hotter it is, the more efficient there is, and then we can burn that gas, which then creates more heat, which then releases more gas. So there's a feedback loop here. So if you have a fire inside a stone chamber, you create a feedback loop. The stones get hotter and hotter, so the fire gets hotter, so that the fire burns at a hotter temperature and becomes more efficient, and the stones get hotter, which drives the whole process forward. So this is why when we cook in an oven, we get much better combustion. Here, look, here's a similar one. So this oven doesn't have a chimney. Air is sucked in at the bottom, fire's inside, so fresh, and it's burning, creating heat. Warm air expands, so the air leaves, which draws in more air. But the air coming in is coming in, so it is rushing in at the bottom, and it hits the back of the oven, and the oven is domed. So to leave, the air has to go slightly further, which means it speeds up. And so the air rushing over the embers of the fire make that fire go hotter. The hotter it is, the more heat it releases, the more it amplifies that effect. This is why our Lorena stove works so well. It's because it has controlled airflows and thermal mass. But we'll come to this. Here's that, looking into that mouth of that oven, and you can see air's been sucked in at the bottom. It's accentuating the fire, and then you're seeing the heat coming out of the top. And that is wood burning at 1,200 degrees centigrade. So a normal fire burns at 400. In this oven, it reaches a temperature of 1,200 degrees, and you have complete combustion. And that's why the oven is so big, and because it has to absorb all of this heat, and it stay hot for several days. So this is how we combust wood. To make wood combust efficiently, we have to make it really, really hot. We can make it really hot by blowing air over it. That's basically what I'm telling you. There's 2 stages to the combustion of wood. As we heat it up, it gives off gas, hydrogen, methane, and also like creosote, like oils that are flammable. And that's the wood gas element. That burns at 550 degrees centigrade. And if there's no oxygen, we're just making the fuel hot. It can't burn because there's no oxygen. So it gives off these gases and leaves behind a pure carbon residue. That's biochar. It's 100% carbon. This could become very, very valuable. And there's many high value things we can do with pure carbon. So just adding it to soil is actually the low value use. There's many other things we can do with biochar. There's a lot we can say about this. And I'm introducing this subject to you today because it's an example of something that connects everything together again. So yeah, it looks like charcoal, but it's not dirty to handle. If you've made it well, it tinkles like glass and it's not oily. You should have driven off all of those oils and combusted them. So, and this is a wood gas flame. This is what it looks like when you create the right conditions to get the wood gas, and that's wood gas mixing with lots of oxygen. And you get an orange, bright orange flame and no smoke. If you're getting smoke, you haven't reached the optimum temperature yet. That's feedback that you're getting from the system. So a really efficient combustion of wood gives you the wood gas, and which perfectly burns and leaves no smoke. So you then have a choice. You can drive the gases and burn the gases, and then decide to either retain the charcoals, and use them for something else, higher value use, like soil improvement, or you can also combust them. So in this system, in this kind of oven, old-fashioned oven, we'd call this a faggot oven. A faggot being a bundle of sticks, narrow diameter sticks. We throw those in, they burn hot and fast, create a lot of heat. So the wood gas dries off, kicks off the whole process, raises the temperature to 550 degrees centigrade, and then the charcoals will burn. And if there's air blasting over the charcoals, they go up hotter and hotter, up over 1,000 degrees centigrade. So there's a 2-part combustion. There's the wood gas and there's the charcoal. When in the biochar world, we use the wood gas to make the charcoal, and then we turn the combustion off. We come up with methods where we can control the combustion. So look, here's a good way to control the combustion. You put your wood inside a metal canister. You can now control the burn process. And there's the wood gas coming out. We know that we've reached optimum temperature, and that this system will keep growing until it's driven off all of the gas, and then there's no air inside, so the flame goes out and you're left with pure charcoal. You're left with the biochar. We came up with many different versions of making it in cylinders, of cooking with biochar gas, with biogas. There's a lot of different things you can do with this. But I want you to get a feel for the technology, a feel for the process and how it works. And then we're going to start thinking about what we're going to do with the biochar that we made once we've made it. So I'll cut to the chase, and I'll say we've made biochar in containers. Like you say, there's very smart things that you can learn and do, make out of recycled materials. But if you don't have those materials, there's other ways you can make it. And you can make it in a bonfire on the ground. And I'm going to show you that as we go forward, different ways to do it. What's actually important is you understand the physics of the burn. this two-part burn. There's the wood gas at a certain temperature. Once you get it to 500 degrees centigrade, the wood gas comes off. That's when you're getting good combustion. You have to make sure it mixes with the air properly, and you get this beautiful bright orange flame. Okay, so this is what charcoal looks like under a microscope. This is 30 microns. So that's fractions of a millimeter. This is tiny. So I think one of the statistics I read in Albert's book is, imagine a teaspoon of think of the biochar more as a powder, okay? Not lumps of charcoal that you cook with, more like a powder made from waste products like grasses or, any low value thing. The surface area of a teaspoon of biochar is 2 acres because of this, because it looks like this, because it's all tubes and edges and surfaces. And it's within this, the soil microbes can live. It creates habitat. It's like a New York City for your soil food web. You're creating on all of these surfaces which could hold a bit of moisture, hold some air, create the right conditions for the soil life in your soil. That's why. So here's the thing about the biochar is once you've got that into your soil, it's creating that benefit permanently. It's not like adding a fertilizer or some compost that will break down and you'll need to replace it next year. This is creating structure in your soil permanently, ongoing. So I want us to be, we need to pioneer this technique and bring it to millions of people, literally, because, hey, it helps us meet our own needs. It helps us hold soil and water. But in the long term, it contributes to the atmosphere of the whole planet. We're contributing garden, planet, biochar. That's why we called it that. We were really trying to think about what's something that's easy and small that everyone could do that's going to have a massive impact at a global scale. Okay, we've only got a few minutes left, and I'll try and save a few minutes for questions. We're going to explore this graph together, and then I'm going to call it a day. I think we've seen, there's lots more to say, but hey, it's not going to be the only time we mention biochar. Let's explore this graph, and it's a little bit complicated, but this is really worth seeing. Here is the temperature of combustion. 0, 200, 400, 600, 800, 1000, okay? That's the temperature of our combustion. And as we burn our fuel, the amount of carbon in that fuel available to us, obviously some of it's going to get combusted. It's going to be consumed in the process. What this is saying is, for some reason, it goes up a little bit as we get to 200 degrees centigrade. And then the potential carbon to be recovered is going to drop because some of it's going to get burnt. But we're left, as long as when we get to the optimum zone here, in this green area between about 500 and 550 degrees centigrade, you'll see that the amount of carbon levels off. So we're losing about 40% of it. We're retaining more than half, 60%, if we've made our biochar right. What about the pH of it? What's its acidity and alkalinity? Well, it starts off slightly acid, rotten wood, and by the time we've finished, it becomes actually really quite alkaline. On the pH scale, it goes up to 12. A biochar that we made was about 10. So that's something to understand and remember when we're using it as a soil additive. But notice again, is if we're in this optimum green zone, we're cooking our biochar between 500, 550 degrees centigrade is the pH only goes up to about 8.5. So that's about okay. And actually don't know what CEC is, but this is an interesting one. Surface area. The surface area, that's how many of these little micropores we get, is it jumps from, where's the surface area scale? Surface area is measured in meters squares by 1/10 of a gram. So yes, on our wood, the surface area is close to 0. Look here, and as we start to cook it, then suddenly at 500 degrees centigrade, it jumps to 300 meters squared surface area per 1/10 of a gram. So that's where we get our 2 acres from, or whatever it was that I said. So it seems that if we can create the right conditions to have a controlled burn, limited oxygen in the way that we make biochar, maybe make charcoal, we can create this incredibly useful and valuable material with a massive surface area that represents our ability to capture and store 60% of the carbon in a material that we're working with. And okay, there's lots of really clever ways and technologies out there of gasifying wood to separate out the coals from the carbon, from the gas, which then gives us a chance to retain the charcoals after the burn. So we can get further into that. But you can, what I need you to understand is there's an absolute optimum zone. And to create that optimum zone, to make our biochar, we need to control the burn. So whether we're using it in a vessel, in a pit in the ground, that's what we're doing. But if we get it right, then we create this massive surface area gain. So you can see, if you don't reach the right temperature, it's not quite hot enough, the magic doesn't happen. But we can see if we get it right, suddenly everything tips our way. And then now we've got a wonderful material that... So here's some biochar made from grasses. They've done it in a tablet that's been squished together, and it's been pyrolyzed, and now we crush that into particles and mix it with compost. Bring it into your food growing systems. It enhances the soil by creating microbial habitat. These are experiments I'm now doing at Trevlack Farm, and I need to experience this for myself. It's taken me years to get to a situation where I can do proper soil testing experiments because it's complicated. But what we know is that we can make big increases to yields and to soil carbon, and I'm trying to get some statistics on that. So bear with us as we learn and grow, and yeah, I guess the object of this exercise was to encourage us to think about how to bring our product to market. I think what we came away learning is we don't want to bring it to market. We want to give the information to people so they can make it for themselves, because we don't want to hold anyone back from being able to meet their own needs, build soil, stack away carbon. That's what we're all here to do. That's our primary function in permaculture. Think about that relationship between garden and planet. What we do locally affects the global system. Everything's connected. Come on, guys, let's work together. Your thoughts, Mr. Jagway?
Wow. This is one of the topics. Anyway, I think the team is getting used to it now, that each topic seems to be my favorite, but biochar and soil in general are my favorite topics. It's really, really amazing how multifunctional biochar and also its evolution from the entire story of the Amazon, and then Terra Preta, it's really amazing. I've had a chance to apply this practically, and you know, this is gold in its own. It's black gold, as they call it. Lots and lots of uses. Most of you are buying it, you know, expensively in pharmacies. When you get stomach aches, you go and buy, is it charcoal tablets and all that? But you have it lying idle at your place, it's biochar. If you have this livestock, let it be cows or pigs or any livestock, you mix it into the diet and the benefits are endless. You add it to compost, endless. Place it anywhere, use it for water purification or the recycling. And, you know, it's just amazing. I think I could talk all day about biochar. So try it out. And there is lots of materials out there that you can read and, you know, try to do the practical, you know, making it by yourself and then also applying it.
What Albert does is he just makes small batches regularly. And he does it in a pit in the ground he's constructed. I could show examples of that. That's Albert Bates who wrote the book. And he's just continually making small batches and then using it in his garden locally. And that's a great way to do it. We could explore lots of other options. But the material that you're using is low value kind of waste. And, you know, our friend Andrew Kalema, Talent Agroforestry, he propagates bamboo plants, which means he ends up with a lot of offcuts of bamboo, which he pyrolyzes into biochar. I'll show some photos of his thing in next week's or future lecture. But I want to introduce his ideas to you. But again, think about how this sits within the notion of systems. Everything's connected to everything else. And think about how important the soil is, the soil mycelium, and then think about what happens when we bring that to life. That's how we now energize a whole system, by bringing that soil to life, stopping to compact it, making sure, removing the limiting factors. You know, that's actually what our strategy is. And then as it comes to life, we suddenly have many more potentials and options. We kind of create our own opportunities through these actions. Okay, great. Well,
any questions, any final thoughts from the team? Peter, Carol, Deborah. I like the garden where Deborah is standing. Brilliant. It's well fed. It should be having bits of biochars in it.
Yes, please.
Hello.
Hi there. Oh, yeah. Hello. Was that just a quick hello, goodbye, was it?
Jogo nego nyako no na.
Oh, Caroline.
Yes.
Oh, please, you're welcome to contribute.
Yes, thank you very much, and a good evening to everybody. I'm sorry I joined the class late because I was en route from Busia, you know, coming from Nakivale. So I tried to log in at about 7:30 East African time, but I couldn't. So later on, I realized that the class was on. But it is good that the recording has been done, because Biosphere right now in Kenya, I'm seeing everybody, all the permaculturists are concentrating on it. And I would, I really want to know what the secret is, and probably share it also in our upcoming PDC, which is starting on 17th of April. I will go back to the recording, do a lot of research on my own, and if there are questions, they'll be coming in the next session. Thank you.
Great, thank you, and you're welcome for that. And we will keep enlarging on this. I think for a lot of these topics, they're too big just to have one lesson. So we'll keep going deeper on biochar, how to make it, how to use it, and its potential, its potentials. So that's great. That's really great. And yeah.
Thanks, Caroline. We look forward to bits of updates from the trip, and sure, you will have access to the recordings. Steve, over to you to close the session.
Okay, just to say I look forward to seeing everyone next week, and I'm trying to bring it more now into examples, and sort of understand how the theory applies to real world situations. That's where we're going now. But we've got a long way to go. But this is our first term. We've done our first 4 principles, and we did a little bit of revision as well today. So do go back, go through your notes, use the links that we suggested, and look forward to seeing you next week.
Thanks,
Okay,
Steve.
bye everybody.
Bye. Thanks, Steve, and thanks everyone. See you then.